In this video, we're going to highlight some important features about work, about the projection vector, about force and displacement, and how they're all related to each other. So let's consider a displacement vector and a force vector that is in a different direction, an applied force that is in a different direction than the displacement. Let's also consider a light that is shining down on the tip of the force vector and casting a shadow down onto the displacement vector. Now remember, this shadow vector is called our projection vector. So let's draw the projection vector that is in the same direction as the displacement, so long as the angle in between force and displacement is less than 90 degrees. Now hopefully from trigonometry you can remember that we could decompose this force vector into the sum of two vectors, one of which is perpendicular to displacement and the other would be in the same direction as displacement. What this means basically is if I were to add the projection vector to this other vector that is perpendicular to displacement, the sum of these two vectors would be my force vector. So this force vector can be decomposed into these two. Now, the projection vector, one of the vectors that F could be decomposed into, is what we're going to consider to be the net force, or essentially the component of the force vector that is moving in the same direction as the displacement. This net force, this projection vector, is the component of the force vector that is causing the displacement. The other component of the force vector is perpendicular to displacement, and so that one is not contributing to the movement. The vector that is perpendicular, the component of the force vector that is perpendicular to displacement, does not contribute to the movement. The only component of the force vector that contributes to the motion is this net force, which is the same as the projection vector. So remember, at our most basic definition, if the applied force is in the same direction as the displacement is, well then we would say that the work is obtained by magnitude of F times the magnitude of the displacement. Well, we're looking at, instead of mag F, because we can't use mag F, that's in a different direction, but we could look at the magnitude of the projection of F onto D multiplied by mag D. Well, that's basically my net force, right? So the work is the magnitude of this projection vector is the magnitude of the force in the direction of D, and then the magnitude of D itself is the overall displacement. So the work is obtained by isolating that component, isolating that projection vector and its magnitude, and then multiplying that by the overall displacement. Well, let's remember that the magnitude of the projection vector is basically the component of F onto D, right? So that is the signed magnitude of our projection of F onto D. And the component of F onto D's formula, we calculate that with this formula here, F dot D over mag D. This, of course, is a scalar quantity representing the length of that projection vector. And you see that if we take F dot D over mag D and then use that as a multiplier with magnitude D, these two magnitudes are going to cancel each other out, and what we end up with is F dot D. Well, we already knew that work could be calculated with just the dot product of those two vectors. We also knew and had a formula for the work if we were given the magnitude of F and the magnitude of D times the cosine of theta. So these are our two main formulas for calculating the work. What we're doing in this example is coming at it from another direction and saying, yes, we understand and we know that this is our formula to give us our work. But that can also be interpreted as the magnitude of this projection vector multiplied by the magnitude of the displacement. And essentially that's saying that this projection vector is the component of the force that is moving in the same direction as the displacement. That magnitude of that projection vector can be considered the only piece of the force vector that matters. Now, fortunately for us, we don't have to consider all of that. This is kind of a theoretical discussion. In order to calculate the work, all we really need to do is dot product the two vectors, and then, or we would have the other formula for calculating the work. Also, we notice that if the displacement vector and our force vector are perpendicular to each other, then we would say the amount of work being done by this force is zero. This force is not contributing anything to the displacement, and there is no work being done by this applied force. And that's true whenever the two vectors are perpendicular to each other. That would be calculated as well if we had mag F, whatever the magnitude of that vector is, mag D, whatever the magnitude of that vector is. But if we have the angle in between the two vectors as 90 degrees, we'll remember that the cosine of 90 degrees is 0, and so it actually calculates out to give us a work that is 0, and we'll just go ahead and put joules down here. But the reason why is because when we project the force vector down onto the displacement vector, there is no projection. There is no shadow here. So there is no component of the force vector that is causing that displacement in the direction of D, and we would say no work is being done by that force.